So, welcome to the waves revision video. What you're going to need is about 2 hours of free time. The total video content is about 1.5 hours, but you want to pause and think about things. Don't just watch it straight through. You could also watch it in chunks. What you'll see is, on the next slide when you get there, is that the total content of waves is shown across the top, and the red box is what is shown for that particular part of the video. So you can skip forwards and find the bit that you're particularly interested in, but it might be worth watching the whole thing and drawing out the mind map in one go. What I do is I write a mind map and summarize everything in the whole of the waves topic. So if you want to do what I'm doing and draw a big mind map, you'll need a sheet of A3 paper. You might get it onto A4, but you're going to have to write really, really small in order to do that. Also, I'm going to be using 4 different colors of pen when I'm doing this. So I would advise trying to find those as well so that you can mimic what I'm doing. Generally, black and blue are for key bulk text. Black is the important headings, blue is kind of slightly less important stuff. Red, I put red boxes around anything that's crucially important, and I usually draw light rays in red as well. And then the green I use for annotating anything else that might not be quite so important. You might read later, so they're annotations, things like explanations of things. I'd also have to hand a copy of your Waves and Optics booklets, the formula sheet, and the textbook to refer to. When you're ready, move on, and hopefully it's useful. Thank you very much. Okay, so this is section 3, waves. We started off by looking at progressive waves and basics of waves. So, have a look in your booklet and see if you can figure out what we covered in lesson 1. I would go and pause the thing here so that you can actually look it up yourself. If you look it up yourself, you're much more likely to remember it in the exam. So, possibly the first thing that comes up is longitudinal and transverse, which are 2 different kinds of waves. So we've got longitudinal waves and transverse. And we could draw some examples of these. So longitudinal ones are ones where we have compressions, bits that are pushed close together, and then bits that are further apart. A bit like, say, rings on a slinky, and when you push a slinky forwards and backwards, so the oscillations of the rings are in this direction, then you get a wave transmitted, and bits of the slinky are close together and bits of the slinky are further apart. The distance from, say, one part on the wave to the same part on the next wave here is called a wavelength. The transverse wave, the oscillations are side to side. Imagine getting a string and waving it up and down. You get something, the string will do something that looks a bit like that. And again, the distance from one point on one wave to the same point on the next wave is a wavelength. Now we could give some examples of this. I'll use green for examples. So transverse wave, all EM waves are transverse. That's light, radio, gamma waves, and so on. Sound is the obvious choice for longitudinal waves. You could also have waves on a string here. Okay. We have defined wavelength. We should also define the amplitude, which is the height from the equilibrium position to the highest or lowest point, amplitude, and that will be the same as that. So either of those would be amplitude. Now, with regards to the longitudinal wave, it's how much in either direction the particles vibrate from the equilibrium position. Okay, so we've done longitudinal and transverse waves. We should also define some other keywords besides wavelength. So we might have frequency. which is, well, see if you can come up with your own definition for it. What is frequency? If you said the buses were very frequent, you would mean that there are a lot of buses, say, in an hour. So if the waves are very frequent, we have a lot of waves per second. And that's what we define the frequency as. It's waves, complete waves per second or per unit time. And waves per second is the unit, or it's also measured in hertz. Now, let's do an example of how to work it out. Supposing that your time for one wave, well, we should define that. Let's just draw that down here. Time period is the time for one wave. So supposing the time for one wave, this should be measured incidentally in seconds, is 2 seconds. How much of the wave will pass in a second? Well, if it takes 2 seconds for a whole wave to pass, in 1 second, half the wave will have passed. So we'll have half a wave per second, or half a hertz. Supposing the time was 4 seconds, well, that means in 1 second, only a quarter of that wave would pass. It takes 4 seconds for the whole thing to pass. So we're going to have a quarter wave per second, or a quarter of a hertz. Supposing instead the frequency was 2 hertz, we have 2 waves every second. What's going to be the time for one wave? Well, if we get 2 waves in a second, the time for one must be half of that. Which is half a second. And if we have 4 waves in 1 second, then each wave must take a quarter of a second. So we can see by looking at this that we can derive a relationship between frequency and time period. And we can see that frequency is 1 divided by the time period. So if frequency is 2, if time period is 2, frequency is 1 over 2. If time period is 4, frequency is 1 over 4. Or we could rearrange that to give time period is 1 over frequency, such as in the second 2 examples. And that's what frequency means and how it's related to time period. Wonderful. There is another formula that we covered in the very first lesson as well. And that's the formula for wave speed. And that's the number of meters that a wave travels every second. So let's do a little example, another example. Let's imagine that we had 1, 2, 3 waves every second. So that's going to be 1 second's worth of time. And let's supposing that each wave was 2 meters long. Then the total number of meters it goes past in that 1 second is 6. 2, 4, 6. So 3 lots of 2. So therefore, speed is 6 meters every second. So what did we do to get that? Well, speed is 3 times 2. 3 is the frequency, 2 is the wavelength. So the speed of a wave is the frequency multiplied by its wavelength. The only other thing you need to know is that speed of waves, light, and all electromagnetic waves travel at the speed of light in a vacuum, and you can look that up on the formula sheet, so you should pause the video and just look it up now. And that's 3 times 10 to the 8 meters every second. You'll be expected to look that up and use it. Right, that's all for the first bit of waves. Let's move on to the second lesson. Okay, so the second bit was on polarization and phase. And again, it's always a good idea to go away and have a look and refresh your memory before going through this bit. So let's start with polarization. Imagine you have a transverse wave. That wave could oscillate up and down, like so. And this is where it gets a bit tricky, but let's just imagine drawing a kind of plane coming out the page like that. The wave could also oscillate backwards and forwards in that plane like that. Imagine that we could also draw a plane kind of coming out like that at 45 degrees. We could also have the thing oscillating like that. Or any other particular bit or angle that we could possibly think of. And the end result is something that looks very, very messy. So let's draw the original plane in as well. So to clear that up a little bit, we draw it like this, and we say, well, there's your up and down oscillation. Have an oscillation like that. In fact, the wave, imagine looking end down at it. Let's draw an eye in here. So if you look down the wave, you would see some bits going up and down, some bits going left and right at any and all other angles. Okay, so let's imagine we've got our wave. That's going up, down, left and right, and so on. And then we put it through a grid. And we end up with only one plane of oscillation coming out. And we call this a plane polarized wave. The oscillations are only in one dimension or one plane. Oscillates in one plane. There we go. Now, what could cause it to do this? Well, in the exam, you'll be given something called the transmission axis, which I've drawn on here. And that's the axis or plane which this particular grid, we call it a polarizing grid or polarizing filter, will transmit the light at. So what's actually going on? Well, this is composed on lots and lots and lots of lines, and the lines are horizontal, contrary to what you may well see in the textbook. And if we zoom in a little bit and see what's going on, if we've got a bar going across like this, let's draw it a bit bigger. So there's the first bar, and there's another bar down there. And the bar is full of electrons. And when the wave comes in, back and forth and back and forth, it drives the electrons backwards and forwards and absorbs, the electrons move backwards, absorb the horizontal bit. This is a little bit more depth than you actually need to know. Electrons in the bar absorb the component of the light, leaving only the vertical bit going through, because the electrons in the bar can't move up and down. They're trapped to go left and right in the bar. So if we take another grid and put it here, now we've only got the vertical bit gone through, so we put some vertical lines here like this, a grid orientated vertically, then the light will make the electrons move up and down. The up and down bit of the light will move the electrons up and down in the wires, and that will be absorbed as well. And the end result is that we'll get nothing out the other side of this second grid. Incidentally, if it absorbs the up and down bit, it must transmit the left and right bit. So we can draw on the transmission axis there. In the exam, you will only be given the transmission axis. You won't need to know about the directions of the bars, but that's how it works. If you have one polarizer, you absorb all but the one particular component of the light. And if you cross them over, you get nothing out at all. Now you could rotate those polarizers and you would absorb different bits. So if you had two that were rotated, and supposing they started off in line, so let's say that they were both vertical, with the transmission axis horizontal there and horizontal there, then the left and right bit of the light would go through, and it would go through here. Now if you rotated this one until do 90 degrees, then what would happen to the intensity of the light if we drew that on a graph? It would start off at some maximum, and it would drop down to a minimum, like that. And then it would gradually rise up again, like so. So this is angle, that's 90. Let's just extend that a little bit so we can see a bit more, oops, what's going on. 90. To 0. 180. That's when it's back in the same orientation. And then 270, and finally, can't mark this on now, that would be 360 there. We've done a full circle and we've been back to the maximum again. So that's polarization. What can you use it for? Well, let's imagine that you had, let's give ourselves a heading over here, uses. So let's imagine that we have a surface of a pond here, or a swimming pool because it happens to be rectangular, and we've got some light coming in, and that light has a horizontal component like so, but it also has, let's try drawing this in a different color. Let's do it blue. Nope, that'll look like the water. Black. We also have a vertical component of the light as well. Now it just so happens that when the light hits the surface, the bit that is parallel to the surface, the horizontal bit, is reflected. And the bit of light that is perpendicular at 90 degrees, so the vertical bit, is transmitted, and that might be transmitted, here we go, down to the bottom of the swimming pool, say, down there, which then might be reflected back off and back out. Okay, vertical bit, vertical bit, vertical bit. So, if you want to block the reflection from the top, to block the reflection, you need to absorb the horizontal light. So if you have a pair of sunglasses like this, with a polarizing filter, where the grid is orientated that way, or the transmission axis is orientated that way, the grid will absorb the horizontal bit, because the electrons can move horizontally in the grid and absorb it, and it will transmit the vertical bit along the transmission axis, which is the bit that's reflected off the bottom. So if you absorb the bit that's reflected off the surface and only transmit the bit reflected off the bottom, then you don't see a glare anymore, and you can see through and to the bottom. And that's how sunglasses, polarized sunglasses, work, but also polarizing filters on cameras. You might also see, less people have TV aerials now, but if you had a look at a TV aerial on the roof of a house, you would see that all the bars on the TV aerial are horizontal, and that's because TV signals are polarized in the horizontal plane. Okay, so that's polarization. Let's have a look at phase. This is going to be important in a couple of lessons' time. So if we have two waves, 1, 2, such that their peaks and troughs line up, we say that they are in phase. Now, supposing instead that we had, let's just change the color, a peak and a trough, such that the peaks and the troughs lined up, so a peak here lines up with the trough here, then we say they are out of phase. Now we need a way of measuring how much out of phase or how much out of sync or how shifted they are, if you like, these waves are. So what we do is we say a whole wave, actually let's draw this at the bottom, one wave is equal to 360 degrees, and in radians that's 2 pi radians. And from there we can work out what fraction of a cycle they're out. So if this is half a cycle out, that must be 180 degrees, half of 360, or half of 2 pi is pi radians out of phase with each other. Supposing instead, let's draw another one, let's draw a green one, there's our original wave, and let's shift it by quarter of a wave. It's going to be a bit harder to draw, so if ever you have to do this, draw the lines down, and we're going to move that quarter of a wave forwards to there. So I'm going to start here, high point, midpoint, low point, and so on. That would be how to draw a wave quarter of a cycle out of phase. And a quarter of a cycle would be 360 over 4, which is 90 degrees, or 2 pi over 4, which is pi over 2 radians out of phase. We don't leave phases in terms of fractions of a wavelength. We don't say a quarter of a wavelength. We always leave it in degrees or in radians. Now, this is a difficult bit, and it's a slight aside on polarization. It's really quite tricky, so don't worry if you don't follow this, just skip forward to the next bit. But supposing we had our scenario at the top here, but let's supposing we had one orientated horizontally, grating or filter orientated horizontally, one over here orientated vertically, and one here orientated at 45 degrees. Does not look like a 45, but never mind, 45 degrees. So what happens? Well, you'd think that you would get nothing out, but that's not actually the case. So the first one absorbs the horizontal bit. Let's mark the transmission axis on. So the vertical bit goes through. And in fact, we're just going to draw that like that. So we have vertical bit going through. Now, this is where it gets a bit interesting, because in the middle, we've got a vertical bit, but the line of the grating is orientated at 45 degrees. So we're going to have to split that into two bits. We've got a bit component of that wave at 90 degrees to the wire, and a component of the wave parallel to the wire. So the parallel bit is absorbed, leaving only the perpendicular bit to be transmitted. Now, let's have a look what happens next. So we've got a transmitted component, that bit there, and now we have vertical lines like this. And again, if we split that component into a component at right angles to it and parallel to it, you see that bit's absorbed, but there is still a component here that is transmitted. That's really, really hard to get your head around. So the end result of all of this we've got a bit oscillating like that, and then we've got an even smaller bit that's oscillating in the horizontal direction there. Again, I've only seen this in one of the examples in the new textbook. It's really, really hard, and if you didn't completely follow it, don't worry. If you've got any questions, come and find me later on. Right, okay, let's move on to the next bit. Okay, so then on to the next lesson. This is on superposition and standing waves. So let's draw a line under the previous one. So lesson 3, which is superposition, standing waves. And it leads on from the bit on phase. So imagine we had a wave. In fact, imagine that we had two waves that were in phase, such that the peaks and the troughs lined up. If you had those two waves in the same medium, in other words, they're traveling through the same thing, so that could be two waves on water, for example, or two light waves traveling through the piece of glass, or whatever it might be, they add together. We call it interference. So we would end up with something that first wave plus the second wave would give us a wave with twice the amplitude. So we go up and down with twice the amplitude. Now, if we had two waves that were out of phase, let's draw these in black. So we had one like that, and we had one like that. This time a peak lines up with a trough. If we added the two together, we would get nothing all the way along, because the amount that it is, the top wave is, say, below the line, is the same as the amount the bottom wave is above the line. And those two bits cancel out to give 0 all points along the wave. It's a complete cancellation. Now, it turns out that if you have a scenario where you have two waves like that, and they have to be going in opposite directions. So if we have two waves traveling in opposite directions, then we see something really, really weird. We see that standing wave pattern, where there are points where points on, say, the string. Let's imagine this is the string in the stationary position, and you pluck it and it goes up and down. There are points where there's no movement at all. Let's label those with an N, N, N. There are points where there are no movements. That's called a node. And then there are points that rapidly move up and down here, and we'll label those with an A, and they're called antinodes, points of maximum movement. If you haven't seen this, Google it or have a look through your lesson notes. You should have seen it in the lesson, and you should have definitely set up and done the core practical where you had to see this done. Now, there's lots of different ways of setting up a standing wave. We could set one up, supposing it's a string and it's fixed at both ends. We could set up one like that, or we could set up one like this. Or if we scroll down a bit, make a bit more space, we could set up one like this, where we have one loop, if you will, so it goes up and back down, or two loops or three loops, and these are called harmonics. So this is the first harmonic, this is the second harmonic, and this is the third. The first harmonic was also sometimes called the fundamental. Now, how much of a wavelength is this? Well, the distance between two nodes is half a wavelength. That's also half a wavelength, meaning that from here to here, the length of the string is 2 lots of half a wavelength, which is the whole wavelength. Here, for the third harmonic, the length is 1.5 wavelengths. So you've got to be able to realise that and apply it. They might say the third harmonic is set up and the length of the string is equal to 3 meters. And so you'd expect to be able to work out that therefore that's going to be 1.5 lots of the wavelength. So the actual wavelength itself is going to be 2 meters. Okay, so that's standing waves and harmonics. Now you could also get a point where, say in a flute, where one end is fixed, but the other end of the flute, where the air can rush in and out, is not fixed. There's nothing for the air to bash against. So you have a node at one end of the flute, but an antinode at the other, which means you get a different set of standing waves set up, which would look a bit like this. For the first, second, and third harmonics. So here, the distance between two nodes is still half a wavelength, but the whole length for the top one is 1/4 of a wavelength. The length of the second one is 3/4 of a wavelength. And here we've got 1 1/4. So the total length is 1 1/4 wavelengths, or 5/4. So it's going to be different depending on how your standing wave is set up. You could also have something such as if you hit a hollow pipe with a hammer, where you have 2 antinodes at both ends. And you could set up something that looks, standing waves that look like that. So you really do have to be quite aware of the scenario that you're looking at. Is it something that's fixed at both ends like a string, or is it something which is open at one end or open at two ends? So if we move on, you did a practical on this, which you need to be aware of, which is core practical. So that's, core practical 1 there. And you need to have a quick look back over your notes. If you remember, you had a prism. So you had a string that was fixed at one end, pulley, and some weights there. And you could change the length, some magnets as well. And that was all hooked up to a power supply, which was an alternating current power supply there. And that caused the wire to vibrate up and down. And you could increase the tension on the wire here. And you could measure from the wooden blocks to the prism to get the length of the string. And because it was fixed, that length was half a wavelength. And then you could add more tension and move the prism to some new position towards the right. Let's label that wood. And you can move the prism and measure the new length and thus get the new wavelength. And the idea was that you could find a relationship between the tension and the wavelength, which would give you a relationship between the tension and the wave speed. So you should go away and look up that relationship from your booklets. The formula is C is the square root, so C is the speed of the wave, square root of the tension in the string divided by mu. And mu is the mass per unit length. The unit is a meter of wire. So it's the mass per meter of wire. Just put a box around that. That's not on the formula sheet. They give you something else instead, which I will show you in a little bit. So that's the formula. You plotted for your experiment. Let's just separate that out for a second. You plotted c squared versus tension. If you rearrange that formula, square both sides, that gives you c squared is t over mu, and rearrange c squared over t will give you a gradient of 1 over mu, 1 over the mass per unit length. And that's what you did for your experiment. Now, in the formula sheet, they don't give that to you. They use the following formula. Let's go across for a minute, create a bit more space. They said that's going to be equal to f lambda. And for the first harmonic, as we pointed out, the wavelength is 2 lots of the length of the string. So if we go back, we've got the first harmonic here. That's the length, but that's only half the wavelength. So if we want to get a full wavelength there, that's the first harmonic there. That's the length. So the wavelength is equal to 2L. So the end result is we have frequency is 1 upon lambda square root of t over mu, and they replace lambda with 2L. And that is on the formula sheet. Frustratingly. Personally, I think it's better off to remember that this is equal to the wavelength. And then if you have, say, the third harmonic, you can easily work out the wavelength. And then the frequency of the third harmonic will run over the wavelength multiplied by root t upon mu. And then the formula works for any harmonic, not just for the first. So next we're moving on to refraction and total internal reflection, which is in the optics booklet now. So we've moved on to optics. The numbers are a little bit muddled up because of practicals which take up a lesson. Refraction and total internal reflection. So if light enters, say, goes from air into water, let's just draw a line here to try and split everything up. If light goes from air to water, it will change direction. And we draw a line on at 90 degrees to the surface, which we call the normal line. And it bends as it goes into the water towards the normal line. And when it leaves the water, well, that's a really bad example. Let's imagine it's some kind of, okay. And then we move into, say, glass, it changes direction again. So what's this like? In fact, let's just say that it moves magically back into air and that somehow we have something that can contain that water. Maybe it's an anti-gravity scenario or something like that. So why does it bend? Well, it bends because it slows down. Light travels slower in water or in glass than it does in air. So you cannot use the speed of light, 3 times 10 to the 8, if you're doing things in water. So imagine that you had a car. We're doing a bird's eye view of the car here. Okay, with the wheels on either side. And when it reaches this point here, the wheel of the car that hits the water first, imagine this car is driving into a puddle. The wheel of the car that hits the water first will slow down, and the wheel that's still on the road will carry on at the same speed. This is really hard to draw on here, but the end result is, imagine if you're walking along with both your arms out and someone stood in the way of one of your arms so that your arm hit that person. The arm that didn't hit that person would carry on, whereas the arm that had come into contact with the person would stop and you'd turn. And that's what happens with the car. So we end up with something like that because this one slows down first. The opposite happens when the car leaves the puddle and this time that side speeds up first. And so the whole thing is reversed and the car leaves the water at the same angle as it went in. And that's called refraction, which is the bending of light. Now, before we move on to use some formula that describe that, we need to talk about something called the refractive index. And the problem with this is that it's very easy to lose sight of what it is when we give it a name. So, let's write it out like this. Refractive index is how many times faster light, can't spell light, how many times faster light travels in a vacuum than in the material. So a refractive index of 2 would mean it was going twice as fast in a vacuum than it was in the material. In other words, if it's 3 times 10 to the 8 meters a second in a vacuum, it will be 1.5 meters a second times 10 to the 8 meters a second in material. If refractive index, which is given the symbol n, actually let's do this in green as it's an example. That's definition of refractive index. E.g., if in a substance the substance is equal to 1.5 times 10 to the 8, then n will be equal to 2. We're going twice as fast in a vacuum. How did we get there? We took 3 times 10 to the 8, which is the speed of light, and we divided it by the velocity in the material, 1.5 times 10 to the 8. And that tells us how many times bigger c is than v, the velocity in the material. So that is our formula for refractive index. Now there's a whole derivation that allows you to work out a relationship between the angle the light goes in at, which is called the angle of incidence. Let's call that angle theta 1, and the angle it refracts out at, which we'll call theta 2. And how that varies, that looks a bit messy. How that varies as you move from one material, which we call, let's say, medium 1, which in this example is air, to medium 2, which in that example is water. And it depends on the refractive index of air, N1, and the refractive index of water, N2. Now the formula that describes that is called Snell's law, and I won't derive it here. But I do urge you to go back and have a look at the lesson. And it says that N1 sine of the angle of incidence is equal to N2 sine of the angle of refraction. And that formula is really, really very important indeed. And it's symmetrical, so you can't get it the wrong way round. Now they could ask you to work out the angles, and they could ask you to draw some lines, and they could ask you to work out other angles. So you work out going from one medium to the second medium, and then from the second medium to the third medium, and you have to be very good at trigonometry to get all of that. Now, it turns out that light doesn't always, if you say go from water to air, it doesn't always come out again. So you did another experiment, and this is now on total internal reflection, which shone light into a semicircular glass block. And that way, when the light hits the glass block, it hits at right angles. It doesn't change direction, it doesn't refract. And you found out that eventually, at some angle, which we'll call the critical angle, let's draw that in black. The angle of refraction became 90. In other words, the refracted light didn't actually come out of the back of the prism. So, total internal reflection, or TIR, is when all the light is reflected inside a material. In other words, if we're going from, say, glass into air, we have to be going from a higher refractive index to a lower one. So from something more optically dense, larger n, to a smaller one. And you can work out the angle at which that happens, because if we go for Snell's law again, which is n1 sine theta 1 is equal to n2 sine theta 2, if theta 1 is the critical angle, then theta 2 must be 90. And you know that sine of 90 is equal to 1. So therefore, sine of the critical angle is n2 over n1. And therefore, the critical angle theta c is the inverse sine of n2 over n1. Going from medium 1 to medium 2. Medium 1 is the one we start. Now, if medium 2 happens to be air, you could replace the refractive index of air, if it happens to be air, with 1. And that's how you calculate the critical angle, the angle at which total internal reflection does happen. Now that is on the formula sheet, but if you work it out from first principles, then you have a really good understanding of what's going on, and you won't get n2 and n1 the wrong way round. They might ask you whether or not something does totally internally reflect. And if you get an error, or you might ask you if something passes through and refracts. And sometimes if you get an error, that means it is totally internally reflected. But it might just mean you made a mistake. So you have to be really, really careful with which way round these things are. Now, you can use this phenomenon to send light down an optical cable. So we really are having to go out a little bit this way now. Total internal reflection, which leads us on to optical fibers. If you shine light down an optical fiber, is our normal line. Then the light, when it goes in, bends, reflects, and is transmitted along the optical fibre, as long as this angle here must be greater than the critical angle, which we'll call theta c. And that's really, really useful for sending signals with light, because light travels much, much faster than electrical signals travel in wires. Now, the bit the light travels down is called the core, and the bit that surrounds the fibre is called the cladding. And much like we have to go inside our experiment with the semicircular glass block, we had to go from a higher refractive index to a lower refractive index. So the core refractive index has to be larger than the cladding for this to work. It would work with air though, because any refractive index of the core will be larger than the refractive index of air, which is essentially as near as makes no odds to 1. So it would work without cladding. So what's the point of the cladding? Well, supposing that you had an optical fibre with a nick in it, like so. The light would come in, and then would hit the scratch and leave the fibre, and that would be no good. So the point of the cladding is to prevent damage. But it also does something else. Supposing you had two fibres, fibre 1, then you had another fibre, fibre 2, and what could happen is that you could have some light reflecting down fibre 1, but when it reaches here, it could carry on and be transmitted into fibre 2. So the cladding prevents that from happening. It's called crossover. It stops light moving from one fibre and crossing over into the other one. With the cladding, the light never actually gets into the cladding, so it can't hop between optical fibres. It also provides, or makes it harder rather, for people, if you wanted to eavesdrop and try and extract some signal. So you could use this method to eavesdrop if you wanted to spy on people, and siphon off, if you will, some of the signal, and then you can start reading it. And it makes it a bit harder to do that if there's a cladding around the edge, because you'd have to kind of scrape the cladding off. Anyway, so that's optical fibres and the pros and cons of them. So the next chunk of stuff is on the double slit experiment. So let's go for lesson 5, somewhere over here maybe, double slits. And again, have a look at your booklet and just refresh your memory about what happened. So if you shine light through two slits, we know that the light spreads out. So here's incoming waves, and the light spreads out like so. And there are points when two peaks line up, like so. And when the two peaks line up, this is a really, really badly drawn diagram, you get constructive interference. So if we go back down here, a peak and a peak give you, so here, peak plus peak, i.e. they're in phase, give you constructive interference, which we didn't label actually. So let's just go back and label this as constructive interference. and when the peak and the trough meet and the waves cancel, we get destructive interference. So when the peaks meet, we get constructive interference. So we get a bright spot here. And then at some point, a little bit further on, say about here, let's redraw that in the center. At some point here, we get peak and a trough. So peak and a trough, peak and a trough, peak and a trough, and so on. So at that point, we get complete cancellation, destructive interference. And then at the next point, we get peak and a peak again. So we get constructive interference. And remember that peak and a peak and a trough and a trough, peak and a peak, trough and a trough. So if you get two peaks, you get constructive interference, but also two troughs, you get constructive interference because you get a bigger trough. So at these points here, you get very, very large peak followed by very, very large trough followed by very, very large peak. You get a very large wave, whereas here you get nothing at all. And we get this pattern. Let's just rub that out. Of light and dark fringes, we call them. And the pattern, if we plot intensity, intensity as a function of position along the screen, we get this set of peaks and troughs. That should be a bit higher there. Light patches, light patch, and then points where the intensity drops off to 0. And then we had a look at Y in a little bit more detail. So, if we redraw this, like so, here are our two slits with a slit separation S. If the two waves go straight through and reach the screen in the center, they both travel the same distance. So if the waves arrive in phase here, then when they reach the screen, they will be in phase here as well. And we get a bright patch. Now, to get the next bright patch down here, we have to have a longer distance. The light from the top slit travels a longer distance to get to the screen. So, in order to get constructive interference here, this distance, this extra length, let's do it in blue to match up with the other one. That length there is called the path difference. It's the length or distance that the light from the top slit travels further than the light from the bottom slit. So if we want to get constructive interference, that has to be a whole wavelength. And then those two wavelengths are in phase. And they arrive in phase. And we get another bright point. So there's our first light spot. There's our second light spot. And the point here, one wavelength path difference. And the point here, where there's nothing, so that's a dark fringe, there must be half a wavelength path difference. Because if they start off in phase, and then one travels half a wavelength longer, then the bottom wave is going up while this wave is going down, and you'll get complete cancellation. So that's what's going on. Now, in order for this to happen, we've assumed here that the light at the two slits is in phase. It doesn't have to be, but there has to be a constant phase difference. So it could be in phase, or it could be consistently out of phase by a fixed amount. If it isn't completely in phase, then the positions of those bright patches will shift ever so slightly up or down. So the light has to be constant phase difference, which has a special word. Which is called coherent. The light also, well, it doesn't have to be monochromatic, but usually we use a monochromatic light source. We'll look at what happens if you get a white or mixture of wavelengths. Monochromatic means single wavelength. Doesn't mean single color. Single wavelength. There. Now the way Young did this is he had a single slit before the double slit. And the result of this meant the light from the single slit travelled the same distance to the two slits, the top one and the bottom one, or a fixed distance to the two slits. And so there was a fixed phase difference. The light all came from both slits, all came from one place, which is a single slit. So the single slit makes light coherent. Single slit gives coherent light. And before that, he put a colour filter in. So let's draw in the colour filter. Hopefully your notes look a bit better than mine. So the colour filter makes light monochromatic. Makes light monochromatic. And actually Young, when he did it, used a candle, I believe. So there is, there we go. There is the candle which he used as a light source. Now you can also get path difference. To get constructive interference, we could have they could have no path difference. So in the sensor, path difference is 0. So we could have 0 lambda, we could have 1 wavelength, we could have 2 wavelengths, 3 wavelengths, and so on, path difference, to give us for constructive interference. And that's how we get the different bright fringes. And there's a formula that links all this together. So the distance here we will call d from the slit to the screen. The width from one fringe to the next fringe we will call, let's make that a bit thicker, we will call w for the width of the fringe. And then we can make up a couple of triangles. So I shall highlight triangle number 1 in yellow here with a right angle in there. And I will also highlight another triangle which is this one in here. Now it's a bit hard to draw this because we're assuming that the light rays are coming off parallel. But there is the other triangle in there with the lines going between the two light rays. So I've had to draw a line between the two light rays because we're assuming that if the screen's very, very far away, they look parallel. Anyway, the end result is, if we've got an angle, and this is starting to look really, really messy now, you're going to have to look back at your notes. But that angle there and that angle there are the same. and sine of each of these angles, so is opposite over adjacent. So if we do this angle here first of all, opposite is the path difference, which is going to be one wavelength for constructive interference, divided by the adjacent, which is the slit separation there. And it's also, for the second angle in here, equal to opposite, which is W, over the distance, the adjacent distance, which is D. And that gives us the following formula. W equals lambda D over S, which links the width from the center point to the next point, which is the same as the width of a minimum from one dark fringe to the next dark fringe. So it's the same as that width there. So the width is equal to the wavelength multiplied by the slit to screen distance D there, divided by the slit separation S. So that finishes off the single slit diffraction. Next bit is going to be, sorry, the double slit diffraction rather. The next bit is going to be single slits. And oddly enough, we've just looked at how light from two different sources interfere to produce a pattern on a screen, but light from a single slit does the same thing. Now, it's not immediately obvious how it does this, but suffice it to say, and this is a little bit beyond the syllabus, but that each point here in between the two slits acts like a different source of waves. So you have lots and lots of different sources of waves that all add together in a slightly more complicated way than the double slit one. You have to take into account lots and lots of different sources. If you're interested, come and see me, and it will take me maybe 5 minutes to explain it to you. It is understandable if you're interested. Anyway, the end result is that we do have bright patches and dark patches like we did before. But this time, the width of the central fringe here, W, is twice the width of the ones in other parts. There we go. And the formula for this, because the central one's twice as big, and because instead of slit separation S, we now have the aperture size A, we still have a slit to screen distance. So this is the screen here. That's still called D. This time, W equals 2 lambda D over the aperture. So very similar to the one for the double slits, but this time, because the central peak is twice as wide, we've got a factor of 2 in there. Again, the derivation for this take about 5 minutes. It's all tied in with the explanation of why you get this pattern anyway. If you're interested, come and have a look. The other thing is that the intensity drops off. So if you have to draw this, you have to make sure that the central one is twice as wide and the intensity is lower. Now, we've done something for the double slits. We've missed something out. Now, for the double slits, you've actually got, colour in the walls, you've got two single slits. So as well as getting the double slit pattern, you also get the single slit pattern overlaid on the top. So if we redraw this, there's our screen. And this time, if you imagine we've got the single slit pattern here with a double width central peak, and then we've got the double slit pattern like this. I've probably been a little bit, we should have a few more there. So you've got this double slit pattern overlaid with a single slit. pattern. So these small ones, and so if you draw the double slit pattern, they are, if it was just the interference from two slits, it would be a constant intensity. However, because it's overlaid with a single slit, the two patterns add together. And there's points where you might get here, say, although it should be a max for the double slit pattern, it's not, because it's 0 for single slit, which gives you a total. If you add up, sorry, if you multiply them together, it gives you a total of 0. There's a minimum there, because there's a minimum in the single slit pattern. So that's single slits. Finally, we're going to move on. The last bit for the final chunk, which was the diffraction grating. So, diffraction grating is actually a series of slits, very, very close together. Now, you won't be given the distance between the slits, which let's call that lowercase d. Don't get that confused with capital D, the distance between the slit and the screen. So you won't be given that, probably. What you'll be told instead, that you have a grating with, say, 300 lines per millimetre. Now, how far apart are each of those lines? Well, if you've got 300 in a millimetre, then if you divide that millimetre between all 300 of them, that will give you the distance. Now, it might not be 300, they might give you a different value, but that's how you work out a value for D. If you aren't convinced that's the case, imagine instead our millimetre was divided up, there's our millimetre, and it was divided up into two slits. Here is slit number 1, and then halfway along slit number 2. Now, that's 1 millimetre. Slit number 3 will come in the next millimetre, so each one of these will have a separation of half. Assuming that the width of the slit is small compared to the rest of the gap between the slits itself. Okay. So what pattern do we get? Well, we don't get this fading in and out anymore on our screen. Instead, we get just dots. We get one in the center, and then we get another one, and another one, and so on. And what's going on is actually remarkably similar to what we had with the double slit. The one in the center, all the light goes straight through and all reach here in phase. They all travel the same distance if they go straight through. Remember, they're coming out essentially parallel, and the slits are really, really close together. D is very small indeed. So they all arrive in phase. Now, if you want to go for the second one, then there has to be a path difference. And that path difference has to be a wavelength. For this one down here, there's another path difference. But this path difference is 2 wavelengths, which I now can't draw. But it's the same idea as we had with the double slits. So, 1 wavelength path difference, 2 wavelength path difference, and no wavelength path difference. What's the formula for this? Well, let's have a look at this triangle here. Just go for 2 of those slits. Here's the light coming off. That's our angle theta. Now that angle there is the same as the angle between the light that's coming out of the grating and the normal to the grating there, which is this black line. So those two angles are the same. And if we measure that angle, which we could do by measuring that distance d, and maybe that distance there, which is what you did in your core practical, you can work out the angle theta using some trigonometry. So we know that this has to be some number of wavelengths. This is the path difference. One wavelength, two wavelengths, three wavelengths, all the way up to n, some number n of wavelengths. So if we've got no wavelength path difference, we get the central dot. Let's do this in blue. N equals 0. If we have one wavelength path difference, we have the n equals 1 dot. And if we have two wavelength path difference, we have the n equals 2 dots. So how are these things all linked? This is our thing D. Now, sine theta is opposite, which is some number of wavelengths path difference, divided by the slit separation between the lines, which is D, which leads us on to the grating equation there. So let's just label this slit separation. That's that angle theta, which is the angle here between the first dot and whichever dot we're interested in at some distance between those two maxima. So it's the angle that the light makes. Now, if it's the first dot, we use a value of n is 1. If it's the second dot, n is 2, and we're going to get larger and larger angles. This is obviously the wavelength, measured in meters. Slit separation will be in meters. Now, n tells us how many wavelengths path difference we have, and tells us which dot we have, and it's given a name. And as soon as you hear the name, you'll forget what it means. So this thing here is the number of wavelengths path difference you have to get constructive interference. So is it the central one where you have no wavelength path difference, the first dot where you have one wavelength path difference, and so on. And that is called the order. It's the number of wavelengths path difference that you have. Green, number of wavelengths, PD for path difference, because I'm lazy. There we go. And that's the diffraction grating. Now, what will happen if we have, for all of these things, if we have different colors? Well, for that, we need to know the order of the colors of the rainbow, which is red, orange, yellow, green, blue, indigo, and violet. And then we've got a longer wavelength to a shorter. Longer wavelength, shorter. So have a look at these equations over here. For a longer wavelength, you're going to get wider, and for shorter wavelength, it's going to be shorter. So if we try and do the same thing for blue light, we'd find the central peak here is going to be smaller. And we end up with, and if we drew the green one, we get something that's in between the two, like that. So we'd end up with a rainbow. We'd end up with the colours being separated out. With the diffraction grating formula, here, longer wavelengths will give a larger angle. So with a shorter wavelength, such as blue light, we're going to have a smaller angle, and we'll have blue dots. The exception being in the centre. With the centre, no wavelength path difference. It gives you no wavelength path difference. The angle is 0. All of them have 0 angle. So the blue dot will be in the centre as well. With green, we're going to get a green dot kind of halfway in between. Again, with the exception of the central dot, which hits in the middle. So the central dot will be a combination of all wavelengths. Whoops, that looks like a D. Will be a combination of all wavelengths of the light. So in the case of white light, it will look white. If you just shine red, obviously it will look red. But for everything else, all other orders are spectra, or rainbows if you will, but don't use the word rainbow. And as you can see, we said a longer wavelength will be a larger angle. So the longer wavelength, the red will be on the outside, we bent through a larger angle, and the other colours will be closer. And that's the same thing with the single slit that we saw. The red light had larger width, and if you look at the double slit pattern, you'll see that's the same as well. Longer wavelength, larger width of the maxima in the middle. That is all on waves. What you need to do is go away and finish off your mind maps or your summaries or whatever you've been writing while I've been doing this, and then have a go at as many past paper questions as you can. The important thing is to understand why things are the way they are.